This film is a summary of our new understanding of the causes of cardiovascular disease. Arterial calcification, the cause of heart attack and stroke, is an early form of the Selorsi disease, scurvy. Here we're looking inside an artery, shown in cross-section as an aid to understanding. Two important structures are visible. Firstly, the outer ring of the arterial wall, consisting mainly of collagen and other connective tissue molecules. This ring of connective tissue is covered with a cell layer, which represents the real barrier between the bloodstream and the arterial wall. These cells are also known as endothelial cells. In vitamin deficiency, particularly vitamin C deficiency, two important structural changes occur in the arterial wall. Firstly, the connective tissue ring begins to dissolve because, due to the vitamin C deficiency, not enough collagen molecules can be formed anymore. Secondly, the vitamins are also lacking as bioenergy substances for the cells, causing loss of function and shrinkage. Between the individual cells, millions of microscopically small cracks form. If vitamin C is completely lacking in humans, the arterial wall breaks open within 4 to 6 months and blood leaks out of the bloodstream. Now we can understand how the sailors of earlier centuries died after 4 to 6 months of a diet deficient in vitamin C. They literally bled to death. In this sequence of pictures, you can see how similar the development of arterial calcification is to the processes involved in scurvy. Nowadays, a total lack of vitamin C is very rare, but nearly everyone suffers from a dietary vitamin deficiency over decades. The complete breaking open of the arterial wall and subsequent bleeding to death, as occurs in scurvy, is an exceptional occurrence. What actually happens is that over many years and decades, the arterial wall gradually becomes weaker. Here too, millions of tiny cracks develop in the arterial wall. Because this all happens more gradually than in scurvy, that is over years and decades, the body has time to react. The liver produces extra repair substances such as lipoproteins, small particles which transport fats, shown here in yellow. These penetrate between the cells into the arterial wall and try to repair it. If this process continues, more and more blood fats and other repair substances penetrate, causing the formation of the much-feared deposits. If this plaque forms in the coronary vessels, this eventually blocks the coronary arteries and causes a heart attack. In the arteries which supply the brain with blood, these deposits eventually cause a stroke. In the next sequence of pictures, you can see the healing effect of vitamin C on the arterial wall. If there's an adequate supply of vitamin C, these vitamin molecules penetrate the damaged areas of the arterial wall via the bloodstream and repair it. Vitamin C stimulates the production of collagen molecules, and the collagen ring, which gives the blood vessel its main stability, regenerates. The microscopic cracks between the endothelial cells also heal. Just as the damage caused by scurvy can be reversed by an optimal supply of vitamin C, deposits in the arterial walls can also be broken down. This doesn't lead to a complete breakdown of the deposits in every case, but these self-healing forces are activated in those parts of the arterial wall which are capable of regeneration. As occurs during the healing phase in scurvy, as the deposits are naturally broken down, the vitamin C molecules present in the diet penetrate the arterial wall via the bloodstream and repair it. The deposits of further blood fats and other repair substances in the arterial wall thereby become superfluous. Not only that, the fat particles which are already deposited there are flushed out of the arterial wall. This breakdown takes place, molecule for molecule, over a period of several months. It is therefore a biological process rather than a mechanical one, in contrast to the balloon catheter and other mechanical procedures whereby pieces of tissue often block the bloodstream. The natural vitamin-aided breakdown is a gentle, risk-free process. The blood lipid molecules which are flushed out are transported in the bloodstream to the liver and burnt up there, that is, disposed of in a natural way. In the breakdown of deposits in the arterial wall, not only vitamin C, but also the amino acids lysine and proline play an important part. These amino acids form a type of Teflon layer around the blood lipid molecules and contribute to their release from the deposits. In this way, the deposits in the arterial walls are gradually broken down in a natural manner. This natural breakdown of the arterial calcification has now been confirmed in clinical studies. In these studies, the optimal provision of vitamin programs developed by us ended arterial calcification within 1 year. In some cases, there was a complete breakdown of the deposits. If you look at these pictures, it soon becomes clear that a new medical epoch has begun, and that bypass surgery and balloon catheters will rapidly become things of the past.
Trials have shown a beneficial effect of N3 polyunsaturated fatty acids in patients with a previous MI.
Icosanoid pathways, which can help change the inflammatory milieu in the body. I'm going to show just one slide that's quite a complex slide, but a very nice one that illustrates all of these factors. And this is a slide kindly provided to me by Drs. Wu and Mozaffarian. It's not published yet, but it's a figure in a review article that they're working on. It's the molecular pathways that are affected by omega-3 polyunsaturated fatty acids is the title. And I would note here that sometimes the term N3 is used. It's the same, means the same thing as omega-3, so they can be used interchangeably. The omega-3 fatty acids can have effect on cells outside of the, in the bloodstream actually. These are polymorphonuclear, these are white blood cells. This is platelets. Platelets are the cells that get activated when you have a cut, and they initiate the process of clotting. The omega-3s, when they're on board, will reduce the stickiness of platelets and make your blood less likely to clot, which is a good thing to a point. There is no increased risk of bleeding in people taking omega-3s. That's commonly misunderstood, but that is the case from the randomized trials. We know that there's no increased risk for clinically significant bleeding. Within the cell, this now here is the cell membrane, and the cell membrane is a mixture of phospholipids that are on the outside and on the inside, the outer leaflet, the inner leaflet. The omega-3 fatty acids are part of this membrane when we eat them. When we don't, there's very few in there. There's always arachidonic acid in the membrane, and these long-chain important omega-6 and omega-3 fatty acids are sitting in the membrane. They affect the actual fluidity. The way they've stated it here, they changed membrane fluidity, they modified different segments, and they alter protein function. And the proteins that are buried in the membrane behave differently if the fluidity of the phospholipids around the membrane is affected. So that's one way we think the omega-3s, just by changing the flexibility of the membrane, it changes the function of many of these proteins. Within the cell, again, the omega-3s can be produce both arachidonic acid and long-chain omega-3, EPA particularly, can be used by cyclooxygenase enzymes.